In late 1941, a landing accident removed a newly delivered fighter from the active flight line. The aircraft is Curtiss P-40B Warhawk serial number 4113297. The recovery and restoration objective for this case was not simply returning a clean museum artifact to the sky, but rebuilding a damaged 1942 mountain wreck into a modern flying warbird. The primary constraint governing this objective was that much of the original structural aluminum had been compromised by impact damage, corrosion, and decades of jungle exposure, requiring complex donor integration. The mechanism that originally preserved this specific airframe from immediate destruction was an ordinary peacetime landing accident severe enough to put the fighter inside a maintenance hangar. The United States Army Air Corps took delivery of the aircraft in March 1941. It was assigned to the 19th Pursuit Squadron based at Wheeler Field on the island of Oahu, Hawaii. The aircraft was one of exactly 131 total units built in this specific production batch. During early operations, the airframe accumulated minimal flight time. By the time of its ultimate destruction a few months later, the machine would record only 56 total airframe flight hours. On October 28, 1941, the aircraft suffered a serious landing accident at Wheeler Field. Available airframe histories agree that the damage required hangar repair, although public summaries differ on the exact mechanics. Some accounts describe a wheels-up landing and ground loop, while Project Tomahawk material cited in an airframe dossier says the accident report was not a simple wheels-up landing. Operationally, the result was clear. The fighter was immobilized, moved indoors, and placed into a multi-week repair process involving undercarriage replacement and structural inspection. The primary anchor proof is the surviving airframe history, supported by later restoration records and museum summaries. Those accounts place serial number 4113297 under repair at Wheeler Field as December 7th approached. The publicly available record does not establish every maintenance docket line by line, so the stronger claim remains the accepted chain of airframe history rather than a reconstructed maintenance log. This mechanical confinement introduces the concept of collateral shielding. Collateral shielding occurs when a localized mechanical failure removes a machine from normal operational readiness, inadvertently changing its exposure to a later external threat. The hangar did not remove the aircraft from the battlefield. Wheeler's hangars were themselves attacked, but it shifted the airplane away from the crowded parking lines where fighters were closely grouped and exposed. The cover of the maintenance structure, even as that structure became part of the target, changed the damage pathway that morning. On December 7, 1941, Wheeler Field was subjected to a massive attack. The incoming strike did not focus only on open-air aircraft. About 24 dive bombers hit the hangars, while low-flying aircraft then machine-gun pursuit planes parked in close formation in front of them. The exposed operational fighters on the flight line suffered severe losses under bombing, strafing, and fragmentation. Serial number 4113297 was not safe inside the maintenance hangar. Later restoration accounts state that the hangar around it was bombed and collapsed. But the October accident had shifted its exposure path. Instead of sitting in the open parking lines, the fighter survived inside a damaged structure long enough to become widely described today as the only surviving airworthy American fighter present at Pearl Harbor during the attack. The delay merely postponed the loss of the aircraft. Once the undercarriage was finally repaired, the fighter returned to active duty with a new pilot. How did this preserved airframe succumb to a fatal operational limit just 6 weeks later? A severe altitude limit governed the fatal impact sequence. When a spinning airframe loses usable power, recovery depends on vertical space. The pilot must reduce the angle of attack, stop rotation, regain airspeed, and still have enough height left to pull away from the ground. In this case, the emergency began at about 8,500 feet above sea level, over terrain rising to roughly 2,500 feet, leaving only about 6,000 feet of usable height above the mountain. The aircraft commenced the spin at 8,500 feet, directly over the Koolau mountain range, where the terrain below rose to about 2,500 feet. That left a maximum recovery window of 6,000 feet, a narrow margin for arresting rotation, building forward airspeed, and pulling a heavy fighter out of the resulting dive. Public airframe histories do not confirm the pilot's final control inputs. The safer reconstruction is based on wreckage evidence. The aircraft appeared to have struck the mountain upright while skidding badly. That physical evidence suggests some change from the earlier inverted spin, but it does not prove exactly when or how the rotation was arrested. This lateral skid would have imposed severe off-axis impact loads across the structure. The available summaries support the broader conclusion that the airframe was badly damaged and distorted, while the exact internal pattern of spar, bulkhead, and tail alignment damage is not fully documented in public records. The aircraft came to a violent halt on the mountainside, damaged enough to be abandoned but still recognizable as a P-40B. Shortly after the crash, military personnel reached the remote site. The single confirmed operational objective was retrieving the pilot. Ground crews had to move through steep, jungle-covered terrain to reach the wreck. They recovered Lieutenant Sprankle's remains while the aircraft itself was left in place. Following this initial extraction, the operational focus shifted to the airframe itself. A stark logistical boundary forced an institutional decision. The mountain terrain was completely inaccessible to vehicles or heavy salvage equipment. Removing a multi-ton structural skeleton from a steep, heavily forested ridge required mechanical lifting capability that did not exist. Compounding this physical limit, the ongoing wartime demands meant no manpower or resources could be spared to dismantle a wrecked, obsolete airframe. The military categorized the wreck as an unrecoverable total loss. The recovery team abandoned the wreckage in the mountains. The heavily damaged aluminum shell was left exposed to the elements. What physical state did the skidding impact leave the airframe in as the military abandoned it to the jungle? 43 years of environmental exposure created a severe forensic limitation on the mountain. In 1985, the Tomahawk's remains were rediscovered, and some material was recovered during an initial evaluation and salvage effort. The organized Curtiss Wright Historical Association and Project Tomahawk restoration effort is better placed in 1989, when serious restoration of the recovered P-40 material began. Public summaries confirm the rediscovery and the remote jungle setting, but they do not document the exact search grid method. A safer account is that searchers used available accident information, local terrain knowledge, and physical survey work to relocate the wreckage under the canopy. Finding the crash site initiated an evidence verification process. The salvage team had to connect the material on the mountain to the Pearl Harbor survivor, serial number 4113297. The public airframe histories confirm that identity, but they do not conclusively document that an original manufacturer data plate, still attached to the forward fuselage, was the decisive proof. Once the identity was accepted, the team faced the much harder material problem. The airframe had rested continuously in a tropical mountain environment for more than 4 decades. This prolonged isolation introduces the concept of environment-driven degradation. In a jungle setting, humidity, rainfall, soil contact, and organic decay can trap moisture against aluminum structure. Where aluminum alloy sits against steel fasteners or fittings, that trapped electrolyte can accelerate galvanic corrosion, eating away at the less noble metal. The physical consequences were serious, but they should not be overstated beyond the record. Public summaries describe the airframe as damaged and corroded, valuable as pattern material, and still containing some castings and forgings that were usable almost as found. The machine was no longer a clean, rigid fighter ready for rebuilding from its own primary structure alone. It was a damaged historical core with some original material salvageable and other areas useful mainly as geometry, identity, and evidence. This material condition created a hard operational boundary for the salvage teams. A simple, intact recovery was not supported by the public record and would have risked damaging pattern material and remaining original pieces. The operation therefore had to treat the wreck less like a whole aircraft and more like fragile historical evidence embedded in a mountain. The site presented a severe engineering trade-off. The wreckage was positively identified and historically priceless, but it could not be treated like a complete aircraft sitting on a hangar floor. The heavy center section remained on a remote incline with no road access. How could salvage teams remove valuable but damaged structure from a steep, roadless elevation when the most important handling details were never fully recorded? The exact mechanical lifting method used to pull the heaviest sections of the fighter off the mountain remains undocumented in the available public summaries. The recovery occurred in phases, with some material removed in 1985 and further material recovered in 1989. Because the public record does not confirm the precise sequence of cribbing, cutting, winching, hand carrying, or helicopter lifting, the safest account is procedural rather than mechanical. The team reduced the wreckage into recoverable material, preserved what could be used, and protected the geometry needed for restoration. The final extraction phase is generally placed in 1989, but the inventory language must remain cautious. Some summaries say the remainder of the wreckage was recovered, while an airframe dossier reports a partial salvage and notes that the right wing was not recovered. The operational record therefore supports a narrower conclusion. By the end of the 1980s, enough major material, identity evidence, and pattern structure had been recovered to make restoration possible, but not enough original airframe remained to treat the mountain wreck as a ready structural foundation. Regardless of the exact transport mechanism, the team had recovered historic identity and crucial pattern information, not a ready structural foundation. Once extracted, the problem shifted from mountain salvage to flight-worthy reconstruction. How could a fundamentally broken skeleton ever endure the stresses of flight again? The engineering team faced a stark binary choice upon analyzing the recovered material. The aircraft could remain a static artifact built around recovered historical fabric, or the team could pursue flight by accepting extensive donor integration and new structural verification. Project leadership selected the flight path, initiating one of the most complex structural integrations attempted on a Pearl Harbor survivor. To return the aircraft to flight status, the engineers utilized structural splicing logic. This is the engineering process of combining load-bearing sections from multiple surviving sources to bypass unrestorable damage and form a single continuous airframe. The restoration team used components from two donor P-40 airframes, serial numbers 39285 and 39287. The engineers surveyed the recovered Pearl Harbor material and the donor material, deciding which original parts could be retained, which pieces would serve as patterns, and which load-bearing sections had to be replaced. The critical problem was establishing a new continuous load path. When a fighter aircraft pulls out of a dive, bending loads transfer from the outer wing panels through the wing roots and across the lower fuselage attachments. If the metal connecting these zones is spliced improperly, shear stress can sever the fasteners. The engineering constraint dictated that when grafting a donor spar section to the original fuselage, the alignment of the structural rivets had to meet original factory tolerances. The team used the heavily oxidized pieces hauled off the mountain as three-dimensional templates, transferring geometry from ruined original metal to donor sections so the spliced joints maintained aerodynamic symmetry. Building this composite load path exceeded the capacity of a single specialty in a single room. To bypass tooling and expertise limits, the project adopted segmented restoration logistics. This operational model distributed distinct subassemblies to specialized facilities to solve different technical limits before final integration. The project physically divided the aircraft. Public accounts placed the wingwork with Precision Aerospace in Australia and the engine rebuild with Cascade Engine Services. Fuselage work is attributed to California Aerofab, while final assembly and flight preparation are associated with the Chino restoration community and fighter rebuilders. The exact shop geography differs across secondary accounts, so the safer point is that the work was distributed and then brought back together for final integration. The distributed work still had to converge into one airframe. A tolerance error in a wing jig would prevent the attach bolts from aligning with the fuselage. Years later, the overhauled sub-assemblies were routed to final integration, where technicians mated the fuselage, wing, and power plant into a single machine that mechanically locked donor metal, remanufactured structure, and historic core together. Would this composite assembly satisfy modern flight certification limits? The final threshold of the recovery was no longer historical identity alone, but legal and mechanical permission to fly. The restoration team aimed to produce a flying aircraft, and the final product is described by its museum owner as the last fully restored and flying American fighter that survived the attack on Pearl Harbor. The composite airframe then had to satisfy the practical requirements of dynamic load viability. An aircraft resting safely on a hangar floor experiences constant, predictable static gravity loads. The moment the wheels leave the runway, the physics change completely. The wings must support the entire gross weight of the airframe multiplied by the gravitational forces generated during banking, climbing, and maneuvering. The newly rebuilt wing attach points and central bulkheads had to be accepted as safe for the intended operating envelope. The regulatory threshold was not a modern standard category type certification. In the United States, this aircraft appears in Federal Aviation Administration records as experimental exhibition category, with no type certificate datasheet listed. That means the aircraft's legal flight status rests on special airworthiness authorization, required inspections, records, and operating limitations, not on the same certification basis as a new production aircraft. If the repaired load paths, systems, or documentation failed to satisfy the applicable inspection and operating requirements, the aircraft could not be flown legally regardless of its historic identity. Achieving this flight viability also required precise weight and balance calculations. The physical geometry of the fighter demands controlled mass distribution to maintain stability in the air. The wartime P-40B armament configuration carried 6 machine guns, with 2 in the nose and 4 in the wings. Restoration accounts describe fabricated gun and ammunition can details, but the public record does not prove that exact ballast was installed to duplicate every wartime armament load. The safer engineering point is that the restored aircraft had to meet approved weight and balance data for its actual restored configuration. Every operational system, from hydraulic pressure lines to the mechanical flight control linkages, then had to be tested on the ground before flight. The culmination of this multi-decade salvage and engineering effort depended entirely on physical verification. The engineers ran the liquid-cooled engine to static power, checking for fluid leaks, temperatures, pressures, and vibration. Several airframe history sources place the first post-restoration flight at Chino on January 12, 2007, with Steve Hinton at the controls, although one collection summary gives a conflicting earlier date. Using the more cautious record, the restored aircraft flew successfully in 2007. The takeoff proved that the integrated structure could carry flight loads within its approved operating envelope. The successful test flight validated the massive engineering trade-off made years earlier. Splicing viable donor sections into the historic core preserved the machine's identity while creating an airframe capable of legal, limited flight. Today, the aircraft is maintained and presented as an airworthy survivor, but public records alone do not prove a steady accumulation of flight hours. Its future will depend on inspection finding, system reliability, operating limitations, and the conservation choice that faces every rare warbird. How much flight is worth the material cost of keeping history airborne?